So before we end this chapter, move on to the next chapter, which we're actually skipping to chapter 6, where we talk about the Laplace transform and how we can use that to work with non-continuous functions. Before we go and do that, I want to make a couple of context things, because similar to chapter 3, I want to remind you that we're really only looking at really nice functions. All of this crazy analysis only works for nice functions, and for messier functions, we're really using computers and to find approximate solutions. Those numerical techniques really come into play. But all of these analytical and qualitative techniques that we're doing right now really does lead to a higher level of understanding, a higher level of being able to work with those computational techniques, interpret those computational solutions, and that's really why we're spending our time in this, even though in practice, much of this is actually more complicated. So to kind of bring that home, I want to focus on two special things that we're using in this chapter. And specifically, one of the things that we're using is linearity. We have linear differential equations in this chapter. We need that for the extended linearity principle. So we have no extended linearity principle without this. And what that means, so no extended linearity principle without this. As you might expect, you might need a linear ODE to have a linearity principle. And so being able to find the general solution of the homogeneous version or the unforced version, and then just adding any particular solution to the forced version, that comes from the extended linearity principle. So you don't have a linear ODE, you don't have that. And that's a big problem. So the fact that this is linear does some really, really nice things for us. That extended linearity principle is super useful. And then we've also been dealing with things, at least for most of this section, with a sinusoidal forcing function, a sinusoidal right-hand side of our equation. And this is kind of nice because sines and cosines really do pop up a lot. Anytime you're dealing with really harmonic motion, you can do it with sines and cosines pretty well. You can pretty much model any harmonic motion with sines and cosines. So that one's I don't think quite as crazy of a restriction as long as we're dealing with harmonic motion. But again, a reminder that there's a lot of right-hand sides. There's a lot of non-homogeneous equations that we just can't solve. Maybe they're just really, really complicated. You're not going to be able to guess the answer to super complicated things. Guessing was a lot easier when the right-hand side was an exponential or a sinusoidal or a polynomial, but that gets all very complicated very quickly. And so also in terms of resonance and stuff, that really did have to do with our sinusoidal behavior of our forced response, which comes from the sinusoidal forcing function. But that being said, this is still useful. I talked a little bit about why it's useful, and these things can be applied to other forcing functions. Again, other forcing functions can be approximated by sinusoidal functions. And then also nonlinear differential equations are very often approximated, at least locally, linearly through a process called linearization. So if you want to learn more about nonlinear, that's going to be in chapter 5 of our textbook. We're going to skip it, but it is very cool, okay? But we'll be going straight to the Laplace transform. And that's pretty much it. You finished chapter 4. Congratulations. Chapter 6 will be our last chapter, Laplace transforms, discontinuities, and then we will be done with this introductory course with 500 videos, not quite 500, but a lot of videos just for an introductory course in ordinary differential equations. You can go way deeper in differential equations. You can go into partial differential equations, which are way more of a headache in differential equations with multiple independent variables. But for now, we won't do that. Have a good rest of your day. Bye-bye.